Hello everyone. In this video, I'll be mainly discussing modulation. So first we shall see about modulation and what is its necessity. The purpose of a communication system is to transmit information or message signals. And message signals are called the baseband signal. Now no signal in general is a single frequency sinusoid, but it spreads over a range of frequency called the signal bandwidth. Now suppose we wish to transmit an electronic signal in the audio frequency range, that is the baseband signal frequency less than 20 kHz, or a long distance directly. Let us find what factors prevent us from doing so and how we can overcome these factors. First is the size of the antenna or the area. For transmitting a signal, we need an antenna or an aerial, and this antenna should have the size comparable to the wavelength of the signal. That is, it should be at least 1/4 in dimension to the wavelength, so that the antenna properly senses the time variation of the signal. For an electromagnetic wave of frequency 20 kHz, the wavelength lambda is 15 km. Obviously, such a long antenna is not possible to construct and operate. Hence, direct transmission of such baseband signals is not practical. So, we can obtain transmission with reasonable antenna length if the transmission frequency is high. That is, if the frequency is 1 MHz, then the wavelength lambda will be much lower, which is equivalent to 300 meters. Therefore, there is a need of translating the information contained in our original low frequency baseband signal into higher radio frequencies before transmission. Now, the second factor is the effective power radiated by an antenna. A theoretical study of radiation from linear antenna of length L shows that the power radiated is proportional to L by lambda the whole square. This implies that for the same antenna length, the power radiated increases with decreasing wave, that is, increasing frequency. Hence, the effective power radiated by a long wavelength baseband signal would be small. So, for a good transmission, we need high powers, and hence this also points out to the need of using high frequency transmission. Now, the third is mixing up of signals from different transmitters. Another important argument against transmitting baseband signals directly is more practical in nature. That is, suppose many people are talking at the same time, or many transmitters are transmitting baseband signals simultaneously. All these signals will get mixed up, and there is no simple way to distinguish between them. This points out towards a possible solution by using communication at high frequency and allotting a band of frequency to each message signal or its transmission. So the above arguments suggest that there is a need of translating the original low frequency baseband message or information signal into high frequency wave before transmission, such that the translated signal continues to possess the information contained in the original signal. In doing so, we take the help of a higher frequency signal, and this signal is known as the carrier wave, and a process known as modulation, which attaches information to it. The carrier wave may be a continuous, sinusoidal, or in the form of pulses. So we can consider a sinusoidal wave, and in this case the carrier waves C of t is represented by AZ sine of omega ct plus phi. Where C of t is the signal strength, AZ is the amplitude, omega c is the angular frequency, and phi is the initial phase of the carrier wave. During the process of modulation, any of the three parameters, that is amplitude, the angular frequency, or the phase of the carrier wave, can be controlled by message or information signal. This results in the three types of modulation, that is the amplitude modulation, frequency modulation, and the phase modulation. Similarly, the significant characteristics of a pulse, that is in this case, the sinusoidal wave is replaced by a pulse. And in this case, we can obtain pulse amplitude, pulse duration or pulse width, and pulse position. And these types of pulse modulation are the pulse amplitude modulation, pulse duration modulation, and the pulse width modulation. Now we can see amplitude modulation in detail. In amplitude modulation, the amplitude of the carrier is varied in accordance with the information signal. Here we explain the amplitude modulation process using a sinusoidal wave as the modulating signal. Now let V of t is equal to Az sin omega ct represent carrier wave, and the message wave m of t is equal to am sin omega mt, where omega m is equal to 2 pi fm. Now the modulated signal Cm of t can be written as Cm of t is equal to Az plus am sin omega ct. It can be further simplified as Az into 1 plus am by Az sin omega mt into sin omega ct. Now note that the modulated signal now contains the message signal. That is Cm of t is equal to Az sin omega ct plus mu into Az sin omega t sin omega ct, where mu is equal to the ratio of am by Az, and this is called the modulation index. In practice, mu is kept lesser than or equal to 1 to avoid distortion. Using trigonometric relation, sin A sin B is equal to half of cos A minus B minus cos A, we can rewrite the equation as Cm of t is equal to Az sin omega ct plus mu into AC by 2 cos omega c minus omega mt minus mu AC by 2 cos omega c plus omega mt. Here omega c minus omega m and omega c plus omega m are respectively called the lower side and upper side frequencies. The modulated signal now consists of the carrier wave of frequency omega c plus two sinusoidal waves, each with frequencies slightly different from known as the sidebands. The frequency spectrum of the amplitude modulated signal is as shown in the figure. As long as the broadcast frequencies are sufficiently spaced out, the sidebands do not overlap. Different stations can operate without interfering with each other. Now we can see about the production of an amplitude modulated wave. Now in this case, we can consider the block diagram. That is, a modulating signal and carrier wave are added together and they are passed to square load device, then to band pass filter which is centered at omega c, and we get the AM wave. Now here the modulating signal AM sin omega mt is added to the carrier signal Az sin omega ct to produce the signal X of. Now in the case of a square load device, which is a nonlinear device, it produces an output y of t is equal to bx of t plus cx square of t, where b and c are the constants. Thus, y of t is equal to bam sin omega mt plus baz sin omega ct plus c into am square sin square omega mt plus az square sin square omega zt plus 2am az sin omega mt sin omega zt, or b into am sin omega mt plus b into az sin omega zt plus c am square by 2 plus az square minus c am square by 2 cos 2 omega mt minus c az square by 2 cos 2 omega c plus c into am az cos omega c minus omega m into t minus c into am az cos omega c plus omega m into t. Where the trigonometric relations sin square a is equal to 1 minus cos 2a by 2 and the relation for sin a sin b are used. Now here there is a dz term which is the c by 2 into am square plus az square, and sinusoids of frequencies omega m, 2 omega m, omega c, 2 omega c, omega c minus omega m and omega c plus omega m. Now these signals are passed through the band pass filter, which rejects the dz and the sinusoids of frequencies omega m, 2 omega m and 2 omega c, and retains the frequencies omega c minus omega m and omega c plus omega m, and the output of the band pass filter is therefore an AM wave. It is to be mentioned that the modulated signal cannot be transmitted as such. The modulator is to be followed by a power amplifier which provides the necessary power, and then the modulated signal is fed to an antenna appropriate size for radiation. Now we can see about the detection of the amplitude modulated wave. That is, in the earlier section we had discussed about the production of AM wave. Now we can discuss about what happens at the receiver. Now the transmitted message gets attenuated in propagating through the channel. The receiving antenna is therefore to be followed by an amplifier and a detector. In addition, to facilitate further processing, the carrier frequency is usually changed to a lower frequency by what is called an intermediate frequency stage, which is preceding the detection. The detected signal may not be strong enough to be made use of, and hence is required to be amplified. A block diagram of a typical receiver is as shown in the figure. Now, detection is the process of recovering the modulating signal from the modulated carrier wave. We just saw that the modulated carrier wave contains the frequencies omega c and omega c plus or minus omega n. In order to obtain the original message signal m of t of angular frequency omega n, a simple method is shown in the form of a block diagram. The modulated signal is passed through a rectifier to produce the output. This envelope of signal is the message signal. In order to retrieve m of t, the signal is passed through an envelope detector, which may consist of a simple RCA circuit. So this is the end of this video. If you have got any doubt, please comment in the section below. Thank you.